children. Now you are comfortable with all the terms related to elasticity. In present session, I am going to discuss in detail about the Hooke's law of elasticity and the different kinds of modulus of elasticity. We will solve some numerical problems as well based on these things. So shall we start now? Before starting Hooke's law, first know about what is elastic limit, because this term we are going to use while stating Hooke's law. What is elastic limit? Elastic limit is the upper limit of deforming force up to which, if deforming force is removed, the body regains its original form completely, and beyond which, if deforming force is increased, then body loses its property of elasticity and then gets permanently deformed. So elastic limit is the limit of elastic property, we can say. Now let us come to, here it can be written as limit of elasticity. After this limit is crossed, the material becomes plastic. So this is limit of elasticity. Let us now consider Hooke's law, which is very important to explain any question based on elasticity. By direct experiment with the extension of uniform rods of different materials, it has been established that for many material, within certain limits, the strain produced in the rod is directly proportional to the tensile stress. By now, you are familiar to the terms strain and stress. So the simple linear relationship between stress and strain was first formulated by the scientist Robert Hooke. If we consider stress-strain diagram for the steel, then we find that up to a point that is called the proportional limit, the stress is proportional to strain. So this is Hooke's law. Hooke said that up to elastic limit we can write stress to be proportional to strain. Or mathematically we can write, if stress is denoted by sigma, then sigma is proportional to epsilon. What is this proportionality constant? If we write the equal to sign, there must be one proportionality constant involved, that is known as Young's modulus of elasticity, because that time Hooke had formulated the law only for change in length, so he given this name modulus of elasticity, that is corresponding to the change in length. It is corresponding to longitudinal stress and the longitudinal strain. This is known as Young's modulus of elasticity, after the name of Thomas Young that introduced this constant. And so now we can state Hooke's law as within certain limit, which is known as proportional limit, stress produced in a material is proportional to the strain, and the constant of proportionality is the modulus of elasticity. Now, based on what kind of stress and strain is involved, we can name different kinds of modulus of elasticity. So let us start with the first one, the first being Young's modulus of elasticity. Young's modulus of elasticity, as just now I had said, Y, that is equal to longitudinal stress upon longitudinal strain. So this is longitudinal stress upon longitudinal strength when the change in length is involved. Now write the values. Stress can be written as force upon area, and this is longitudinal strain, so has to be delta L upon L. From here we can write Y to be equal to FL upon A delta L. This is Young's modulus of elasticity. Let us first do a numerical based on this. When a weight W is hung from one end of a wire of length L, the other end being fixed. Let us draw the situation first. It is the wire of length L and a weight is hung from here W. If the same wire is passed over a pulley and two weights W each are hung at the two ends, this time the wire is moving over the pulley and on both the sides weights are W. What will be the total elongation in the wire? Okay, so let us first consider situation number 1. We can calculate if Y is Young's modulus of material of wire, A being its area of cross section, then we can write Y to be equal to, it should be WL, because the force applied is W, so WL upon A into change in length given by small l. From here we can write this small l to be equal to WL upon A into Y. In other case, we can treat either segment of length L by 2 because these are equal weights, so of course has to be symmetric in position. If we consider this length as L by 2 and can think if one of the end is fixed while the other end is attached to the load W, because the point which is in contact with the pulley will remain stationary. So we can consider this end being fixed. Now this time if change in length be L dashed, then we can write Y to be equal to WL by 2. Now the length has become L by 2 upon A into L dashed, and from here L dashed will be equal to 1 by 2 WL upon AY, that is extension in the first case upon 2. So increase in length for both the segment if we consider, that will be equal to net change in length has to be twice of L dashed, it will be equal to L. And as you can see that increase in length has to be same in both the cases, whether only one weight is hung or if the wire is passing through a pulley and the two weights are hung from each side. In both cases, we got extension to be the same. Let us come to one more problem. A load of 10 kN is supported from a pulley, which in turn is supported by a rope of cross-sectional area 10 to the power 3 mm square and modulus of elasticity 10 to the power 3 Newton per millimeter square. As you can see here, neglecting friction at the pulley, the downward deflection of the load is, we have to calculate what will be the downward deflection. Let us first calculate if tension in the pulley be, I am drawing this situation here again, if T be the tension in the rope. So from here this is 10 kN. We can write that 2T should be equal to 10 kN. So T we got as 5 kN. That is the tension in the rope. Of course, this tension will produce a stress in the rope. So we can write stress in the rope sigma as this should be equal to T upon the cross-sectional area. So that will be 5 into 10 to the power 3 upon the area is given 10 to the power 3 millimeter square. So let us write it in millimeter square only. That will be 5 Newton per millimeter square. So extension in the rope, if I write by delta L, that can be given by stress upon Y into the original length. So on substituting all the values, it will be 5 upon Y is given as 10 to the power 3 Newton per mm square into the original length, that is equal to, this is 900 plus 600. So 1500 mm. The answer will be 7.5 mm. And therefore deflection of the load, because this 7.5 mm is the total increment in length of rope, and if this is the increment in length of rope, then pulley will come down by half of this. So the load will be deflected by, I am writing by delta, it has to be equal to half of this, that is 7.5 by 2, which is equal to 3.75 mm. One more illustration is there. A rod of uniform cross-sectional area A and length L has a weight W. It is suspended vertically from a fixed support. If the material of the rod is homogeneous and its modulus of elasticity is Y, then determine the total elongation produced in the rod due to its own weight. Okay, let us do this question. If we consider the rod to be hung like this, one of the end is fixed to a rigid support and this be the length. Now here force cannot be same for the entire length of rod because it is having some mass. So of course we have to consider a small cross section where we can consider force to be uniform. So let us consider a small cross section of this rod which is at a distance x from here, and this element itself is having thickness that is equal to dx. So if we now zoom it out here, the small cross section that is dx, the forces applied will be in lower direction it should be t, and in upper direction somewhat more, that should be t plus dt, because as we know that at the free end tension has to be 0 and it will be maximum at the uppermost end. So when we move upper in the rod along the length, its tension will keep increasing, and for this small length dx, it has been by small value that is dt. So we can write stress for this cross section sigma to be equal to, it has to be weight per unit length into length of the rod that is below it, which is x, upon area of cross section, that will give Wx upon Al. If we consider that elongation produced is d delta, then this can be written as sigma upon y multiplied with the original length for cross section that is equal to dx. On substituting the values, it will come out to be W upon YAL x dx. So total elongation produced, if it is delta, it should be integration of this small elongation. So on integrating this value, Wx dx upon YAL, within the limits, it should be for the whole length. So I am integrating within the limits 0 to L, and the final answer we will get as 1 by 2 WL upon Y into A. This is the total elongation produced in the rod due to its own weight. Let us see one more question now. A uniform rod of length L and mass m is pulled horizontally on a smooth surface with a force F. Let us first draw this situation. This is the uniform rod which is being pulled by the force F. It is put on a horizontal surface as shown here. Determine the elongation of rod if Young's modulus of the material is Y. Now under the action of this external force, of course the rod will accelerate because other end is free to move. It is not attached to any rigid support. So an acceleration must be there, and that acceleration can be written by A is equal to F upon m. The magnitude of stress decreases as one moves away from the point of application of force. So if we consider one small cross section here which is having length dx, from the free end its distance being x, of course from here other end the distance will be equal to L minus x. So if we consider the situation of a cross section which is taken at a distance x from the free end, then to determine the total elongation of the rod, we have to consider elongation in this small element dx. So if consider that force at this distance b, then F dash should be equal to F into x by L, because over the length L the force has been increased to from 0 to F. So for the length x, it will go to value till Fx upon L. And we can write then stress at this section to be equal to sigma is equal to F dashed upon A. On substituting the values, it will be F upon A x by L. If we consider as in the previous question, d delta be the elongation produced in this small cross section, then it can be written by F upon YAL into x and then length of this element, that is equal to dx. So the total elongation produced will be, it should be delta, that is integration of d delta. Now we have to integrate this value, which is Fx dx upon YAL. It has to be integrated within the limits for the whole rod, that will be from 0 to L. So it will give F upon YAL x square by 2. And on substituting the limits 0 to L, this will come out to be 1 by 2 F L square upon YAL. One of the L got cancelled and final answer we got as 1 by 2 FL upon YA. Now let us see one more term, that is known as modulus of rigidity. Now what is modulus of rigidity? This is another kind of modulus. First we had considered Young's modulus of elasticity. The next kind of modulus is known as modulus of rigidity. Whenever there is tangential stress applied, again as I had discussed earlier also, if this be the condition for a block, if its lower end is fixed and a tangential force is being applied on the upper block, then it gets displaced like this. There is only change in shape. So if this value be theta, we can define modulus of rigidity for this kind of shape change. So let us define this. Generally it is denoted by eta. So mathematically this value is equal to, it is tangential stress. For Young's modulus, that was the normal stress. This time it is tangential stress. So it is tangential stress upon the tangential strain, which is also known as shear strain. And as I had said, this shear strain is measured in terms of the angle by which the face has been deflected on which the force F is applied. So if we now substitute the values for tangential stress, it should be F by A upon shear strain that I have shown here as theta. So value will be equal to F upon A theta. This is how modulus of rigidity is defined. This is simply an extension of Hooke's law for shearing stress and strain, because he had derived the law only for longitudinal stress and longitudinal strain. Later this was also added into the Hooke's law, which is known as its extension. Sometimes this modulus of rigidity is also denoted by capital G. So if we have to define it in words, we can say that constant of proportionality is called shear modulus or the modulus of rigidity when we are defining that tangential stress is proportional to shear strain. Its unit again has to be equal to Newton per meter square or Pascal. So it is actually measure of resistance to alter the shape of the body. Now let us see how numericals can be solved based on this kind of shear stress and strain. One illustration is there. A 0.05 meter cube has its upper face displaced by 0.2 centimeter by a tangential force of 8 Newton. Calculate the shearing strain, shearing stress and modulus of rigidity of the material of the cube. So let us see. Length here is given as it is 5 into 10 to the power minus 2 meter. The displacement, that is delta x. Here I am not writing delta L because this delta x is change in length, because this delta x is displacement of the other face for which the force is tangential. So delta x I am writing, this value is given as 0.2 centimeter, which will be 2 into 10 to the power minus 3 meter, and force is given 8 Newton. So if I write shearing strain, that can be written as denoted by theta, its value will be delta x upon L, which is 2 into 10 to the power minus 3 upon 5 into 10 to the power minus 2. That is equal to 0.04. This is the shear strain. Now to calculate shear stress, we have to write F upon L square. So it will be equal to 8 upon 5 into 10 to the power minus 2 and then square of this, that will come out to be 3200 Newton per meter square. So we can now calculate modulus of rigidity as well. It will be 3200, that is the shear stress upon the strain, which is 0.04, and the final answer will be 8 into 10 to the power 4 Newton per meter square. One more illustration I have. A cube of sponge rubber with edge length 5 cm has a force of 2 Newton applied horizontally to the top face, while the bottom face is held fixed. If the top face is displaced horizontally through a distance of 1 mm, find the shear modulus for the sponge rubber. Let us solve this also. We know that this shear modulus can be defined as it should be stress upon strain. So that can be mathematically written as F upon A and divided by, it should be tan theta. Either you can write theta if angle is small, or it can be written as tan theta as well. So let us now substitute the values, but before that we have to calculate tan theta for small angle. As I had said earlier also, this can be written as nearly equal to theta. That will be the displacement, which is given 0.001 meter upon the length, that is given 0.05 meter. So this tan theta, so this theta will be equal to 0.02 radian. Always do write this theta in radian while doing the calculation. Do not write the value in degree. So we can write this G to be equal to, it has to be force upon area into theta. Force is given as 2 Newton. So this is 2 upon 2.5 into 10 to the power minus 3 multiplied with 0.02. And the answer we will get as 4 into 10 to the power 4 Newton per meter square. One more question I have. A horizontal aluminium rod of diameter 4.8 cm projects 5.3 cm from a wall. A 1200 kg object is suspended from the end of the rod. The shear modulus of aluminium is 3 into 10 to the power 10 Newton per meter square. Neglecting the mass of the rod, find shearing stress on the rod and the vertical deflection of the end of the rod. Okay, let us start doing the first one. Shearing stress we have to calculate, so it will be equal to F upon A. Force has to be weight, that is mg, upon the area, which is pi r square. So if I substitute the values, it will be 1200 into 9.8 upon 3.14 into square of 0.024. That will be equal to 6.5 into 10 to the power 6 Newton per meter square, which is the shearing stress. In second part, we have to find vertical deflection of the end of rod. So let us consider that delta x be the vertical deflection. This is the deflection produced in the rod in vertical direction. So we can write now shear modulus of rigidity G to be equal to F by A upon delta x upon L. So from here we will get delta x to be equal to F upon A multiplied with L upon G. And on substituting all the values, it will be 6.5 into 10 to the power 6 into 0.053, and this whole divided by 3 into 10 to the power 10. The answer comes out to be 1.1 into 10 to the power minus 5 meter, which is the deflection produced in the rod. With this, our today's session is complete. Today we discussed Hooke's law and all the kinds of modulus of elasticity. Also, we solved a good number of questions related to this elasticity. So let us look forward to the next session. Till then, please do take care of yourself. Goodbye.